So now we are going to discretize the unsteady heat conduction equation. We have already discretized the 2D steady conduction equation, and from there we will develop now further, and we will focus on the 2D unsteady, although the problem you will be solving is 3D unsteady, but the discretization will follow a very similar procedure. So I will show you as a 2D unsteady problem. So we come back with this similar picture that we have seen for 2D steady problem, but now we have this additional term here. I removed the source term also here, but I think you should be able to take the necessary steps to include the source term. So here my domain is going from 0 to Lx and 0 to Ly for this equation. Here x equals 0 to Lx and y equals 0 to Ly. And the indexes are going to I equals 1, I equals nx, and on y side j equals 1, j equals y. These are the indices. We also assume uniform grid delta x and delta y. They may not be equal, delta x and delta y, but they are uniform by itself. So now we want to discretize this following the same manner we have discretized before. So we start with explicit scheme. In explicit scheme, the right hand side is discretized in nth time step. Left hand side, we have this forward in time n plus 1 minus n divided by alpha delta t here. And then you can see that only uij n plus 1, that is the unknown here. So I can write this difference equation now, uij n plus 1 equals uij plus certain correction, and that correction is coming from this alpha delta t by delta x square of this x direction, and this is from the y direction. So here, this is the point we are referring to. This is my ij point, I minus 1j, I plus 1j, these are these green points. Ij minus 1, ij plus 1, these are the red points. So this is going to be my stencil here. It's not in one-dimensional transient diffusion equation. This was the time axis. Here we are not showing the time axis really. So time axis will be in the third dimension, that will be perpendicular to this screen. So this is all, these are spatial point, and this uij n plus 1, it will be somewhere at the top. So these are all from the nth. So here you can see that it doesn't require any solution of equations. Simple calculations, we can do these simple calculations and solve the equation very easily. This is the technique that we have learned before in one-dimensional case, but now you can see through two-dimensional case. Extension to three-dimension is straightforward. Similarly, in implicit scheme, as we have seen in one-dimensional transient conduction, that the right-hand side here are at n plus 1th time step. Therefore, it does require solution of equation. Each ij will bring an equation that will have 5 unknowns. So unlike the one-dimensional case where each equation were containing 3 unknowns, now we see that each equation will contain 5 unknowns. So overall, it will lead to a pentadiagonal matrix, and we have to find an appropriate algorithm such as Gauss-Seidel to solve this. Here aij's are, you can calculate from here. All of them contain this alpha delta t term. Unlike the steady case, in steady case they are only this 1 by delta x square or delta y square, but now they contain alpha delta t term. Now the PDE is transformed into a system of linear equations. We can solve them using Gauss-Seidel type algorithm, but the main difference with the steady case here, it looks like very much the steady case, but what you see here is that as I go from n to n plus 1th time level, we have to solve one round of Gauss-Seidel. Then I go from n plus 1 to n plus 2, I have to solve another round of Gauss-Seidel. So at every time I have to solve this Gauss-Seidel once. So that is the problem. Overall computation is very high. In the previous problem of steady conduction, we were solving Gauss-Seidel only once, and that was it. But here at every time, you start from initial time n equals 0 to find u at 1, time level 1, you have to solve Gauss-Seidel. Then from 1 to 2, again you have to solve Gauss-Seidel. And you have to keep on solving this. So Gauss-Seidel has to be solved many times. And this is not a very forgiving algorithm. It will take long time in computer depending on the problem that you are solving, especially the boundary conditions or source terms. It might take quite some time in a computer. So this is fundamentally the difference with steady problem, where you solved steady problem, you solved the linear equation only once, but now you have to solve every time. The third one is obviously the Crank-Nicolson scheme. And Crank-Nicolson scheme is very much like the implicit scheme. So here you can see that we have taken half of them as implicit, half of them as explicit. So this is the explicit part, this is the implicit part. And then you will get a similar looking equation here. Only the right hand side will be different than the implicit. But other than that, it will look similar. These a's will be different because of this 1/2 factor here. Otherwise, they are very similar to implicit. The solution methodology is also similar to implicit. GSSOR we have to apply every time. Of course, many such combinations of explicit and implicit discretization may be used, that also we have discussed before. But this is the most common. There are, of course, reason why it is common, because it gives higher accuracy than other combination. Now to summarize, we have discretized the equation for unsteady two-dimensional problem. Now you can develop the discretized equation for unsteady three-dimensional problem in the same manner. The extension should be very straightforward. So before you implement it in actual program, you can develop it here. So thank you. That's all for now, and I'll see you in next class.